All right, let's have a look at the last one. So D. So if we were proving P of 1 is true, we're saying since P of 1 is true since, and if we put it in there, you can see S1 equals A, R to the 1 minus 1 on R minus 1. These cancel and you just get A, and S of 1 is A, so you know it's true for P of 1. We want to assume it's true for P of K, which is SK, so that's A, R to the K minus 1 on R minus 1. And then if we use this recursive here, we know that we want to prove, what do we want to prove true? We want to prove that S of K plus 1 is true, which is, if I put that down here. So A, R to the K plus 1 minus 1 over R minus 1. Alright, so now going to the recursive formula and rearranging it a little bit, we know that that would give us, here it is here, so I'll just put the S of K on the other side, plus AR to the N minus 1. So we can use the assumption, the S of K, so A, lots of R to the K minus 1 on R minus 1 plus AR to the N minus 1. Remember, we're trying to get it to look like that, and that has an R minus 1 as a denominator, so if I put R minus 1 here and times by R minus 1, I've now got a nice denominator of R minus 1, and I also have an A in both of those in common. So if I factorize by A on R minus 1, or they're both got an R minus 1, so if I factorize by A and look at the top, I've got R to the K minus 1 plus R lots of R, that should be a K, shouldn't it? Yep, alright, so it should be, actually, I didn't even sub it in. It should be a K plus 1 minus 1 here, which would just give us a K. So apologies there, that should just be a K. Alright, so now when I'm multiplying those two, I get R to the K plus 1. And then I get minus R to the K there. So you can see R to the K minus R to the K cancel, and I just have what I want, which is R to the K plus 1 and minus 1. So it matches that one. So then you'd say, okay, so that equals my S of K plus 1. That's, so by induction, this is true for all, and N is greater or equal to 1.